In this video, we're going to introduce a little bit more language for group actions. So for this video, let's suppose that we have a group G acting on a set X. So again, the symbol means acts on. And we'll assume that action is denoted by the period symbol. So for example, G period X means the result of G acting on X. All right, I want to introduce two ideas in this video, and those are the idea of the orbit and the stabilizer of an element. Stabilizer. Let's start with the stabilizer. So here's the definition. Given a group action, G acting on X, and some element, X in the set X, the stabilizer of X, that is the element X, which sometimes we'll write stab of X, and sometimes if needed for clarification, we'll call it stab sub G of X. That is, if I want to say what the ambient group is. So this is the stabilizer in G of X. So this is going to be a set of group elements, and here's how we define it. Is the set stab sub G of X equals the set of all G in the group such that G acting on X leaves X alone. So in other words, the set of all group elements that act on X to produce X. All right. Notice this is specific to X. It doesn't have to be the same for every element of the set X. That is, if I change the set element, I may get a different stabilizer. But it's the set of all group elements that leave that particular set element alone. All right. Now I claim that for any X in the set, the stabilizer in G of X is a subgroup of G. And again, this is one of those situations where if you feel like you're starting to get a hang for group actions, you should just pause the video and see if you can prove this. It's like other subgroup proofs. I'm going to approach it the same way. I think for a lot of you, working out the steps on your own might be a nice way of getting familiar with how to work with group actions. I will go ahead and prove it in the video, but you should pause and give it a try. All right, I'm going to move on. So here's the proof. All right, we're going to use the two-step subgroup test. All right, first of all, to establish that the set stab of X is non-empty, I know first of all, we should let X be an element of X, because I didn't do that in the theorem statement. So that comes first. All right, so now that I've done that, I know that the stabilizer is non-empty, because the identity of G acting on X has to produce X. That's a property of group actions. So the identity also always belongs to the stabilizer of X for any X. So that's one thing. Now, the first proper step of the subgroup test is showing closure. So let's suppose G and H both belong to stab of X. We'll show GH also belongs to the stabilizer of X. All right, to do this, we know since G and H both belong to the stabilizer that G acts on X to produce X, and H acts on X to produce X. In other words, G and H both leave X alone. So GH acting on X, how's that going to look? Well, the first thing I'm going to do is I'm going to use my composition rule for group actions. If GH is acting on X, that's the same as acting with H followed by acting on the result with G. Well, G acting on H acting on X, well, H acts on X to produce X. So that's just the same as G acting on X. And then G acts on X to produce X. So in other words, just to put it in the vernacular, I know that H leaves X alone, So x is going to come out of this process, and then g is going to leave it alone as well. So having g and h leave x alone sequentially is going to have the same result as having gh act on x. So this means gh belongs to the stabilizer. Okay, so that's one step. And the other step is proving that the stabilizer contains all of its inverses. So suppose G belongs to the stabilizer. We'll show G inverse also belongs. All right, well, if we know that G belongs to the stabilizer, then this means G acts on X to produce X. But by a theorem that we covered in one of the previous videos, if G acts on X to produce X, and I'm going to write this down, so G acts on X to produce, and I'm going to put another color here, to produce X. So G acts on the blue X to produce the purple X. But now, what do we then know? So we also know that G inverse will act on X to produce X. Because if G acts on some input like this to produce an output like this, then G inverse has to take that output, that is this thing, back to the original input. So G acts on this thing to produce this thing. And that's just a property of group actions. All right, so that means G inverse also belongs to the stabilizer. All right, so now we've shown that the stabilizer is closed under multiplication and contains all of its inverses. So the stabilizer of X is a subgroup of G. All right, now the other thing I want to introduce in this video is something called the orbit of an element of X. So here's another definition. Oops. Definition. So let a group G act on X, and let X be an element of the set X. Okay? Then the orbit of X, and again I'm going to write this in two different ways, written orb of X or orbit of X under G. And again, the reason I make this distinction is sometimes we might want to talk about what the orbit is of an element under a subgroup of G. We're not doing that in this video, but if we want to make the distinction between the entire group and its subgroups, then we need this little subscript notation. So that orbit is the set orbit under G of X equals the set of all Y in the set X for which there exists a group element G such that G acts on X to produce Y. To put it a little bit more tightly, it's the set of all results of G acting on X where G belongs to this group. All right, so in other words, the orbit of X is the set of all objects in X in the set that you can get to by acting on X with group elements. Now, I'm not going to prove any special properties of the orbit in this video, but I do want to do a fairly sophisticated example of stabilizers and orbits. So here is a fairly sophisticated example. I'm going to let my set X be the set Z mod 10. So that's the set of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Really, it's those congruence classes, but I think I can get away in this video with referring to them just by their numerical names. The group acting on this set is going to be U sub 10, and that's just the set 1, 3, 7, 9. It's the set of all congruence classes represented by numbers relatively prime to 10. Those numbers relatively prime to 10 are 1, 3, 7, and 9. The action of G on X is going to be that G acting on X is just G times X mod 10. So for example, 3 acting on, let's say, 6 is going to be 3 times 6 mod 10, which is 8. And I'm using the equal sign very loosely here. I'm going to use the equal sign to mean belongs to the same congruence class, not actually is numerically equal. All right, so 3 acts on 6 to produce 8 because 3 times 6 is 18. 18 mod 10 is 8. Just to have one more example, 7 let's say 9 is 7 times 9 mod 10, which is, well, that's 63, but that's congruent to 3. Okay, so I claim that this is an action of G on X. I'm not going to show that super carefully here, but to show it, we would need to show that GH acting on X is the same as H acting on X followed by G acting on the result. We would need to show that the identity, that is 1 in this case, acts on each element over here to produce the same element. And that should stand to reason. If we multiply something over here by 1, we get the same thing. So that property is not too hard to verify. Now let's talk about orbits and stabilizers. I just want to illustrate that some funny things can happen here. And not funny like anything wrong is happening, just I think interesting is probably a better word. So let's think about what the stabilizer in G of, and I'm going to pick 7, what that would be. What would be the stabilizer of 7? So I can imagine each of my units, because I need to figure out which units will act on 7 to produce 7. So I can work out what each of those would be. 1 acting on 7 produces 7. 3 acting on 7 produces 21, which is 1. 7 acting on 7 produces, I realize as I write this, it looks like I'm writing decimal numbers, which I'm not doing at all. This is period means acting on. 7 acts on 7 to produce 49, which is 9. And then 9 acts on 7 to produce 63, which is 3 in this set. Okay, so first of all, which things are in the orbit of 7? The orbit of 7 consists of 7, 1, 9, and 3. So I can write down that the orbit of 7 under G is 1, 3, 7, and 9, which looks awfully familiar. That's the set of all units mod 10. But it is a subset of Z mod 10. It's not a subset of the group. But the stabilizer of 7 is the set of all group elements which act on 7 to produce 7. And in this case, that is only one thing. That is 1. So in this case, I get that the stabilizer in G of 7 is just 1. It's the trivial subgroup of the units mod 7. But now here's something interesting that can happen. Let's suppose I change the question and this time ask about the stabilizer and the orbit of 5, which is also an element of my set. Remember, stabilizers and orbits are of elements of the set, not elements of the group. So let's ask what the stabilizer is and what the orbit is. So again, I'm just going to work out what happens when each group element acts on the number 5. So let's pick a different color here. There we go. So 1 acting on 5 produces 5. 3 acting on 5 produces 15, which is also 5. 5 acts on 5 to produce 25, which is also 5. Oh, sorry, that's not a group element. 5 is not a group element. And then 7 acts on 5. I just got into odd numbers, I guess. 7 acts on 5 to produce 35, which is 5. And 9 acts on 5 to produce 45, which is 5. So in this case, 5 is stabilized by everything. So the stabilizer of 5 is the entire group. And then the orbit of 5, well, the orbit of 5 is just all the elements of this set that we can get to, Z mod 10, by acting on 5 with elements of G. And that set is just the number 5. So the orbit in this case consists of only one element, and the stabilizer consists of 4 elements. And I want to write this down because there's a nice pattern here that we're going to investigate in the next video. So here the stabilizer had order 1. This is in the first example with 7. And the orbit had order 4. That is, the orbit had 4 elements. But in the second case, the stabilizer 5 had order 4. It was the entire order of the group. And the orbit of 5 had order 1. Well, that's interesting. I think we'll check that out in more detail in a future video, but we need to introduce some other things first. So anyway, that's an introduction to stabilizers and orbits.